Welcome to lecture 32. In this lecture, we're going to talk about unsteady state operations. Just to remind you, we said we have few cases, actually 4 cases, where x is not our preferred variables to be used in a design equation. Therefore, we're going to use the design equation written in terms of molar flow rate, or concentration, or number of moles. And one of the 4 cases is unsteady state operations of non-batch or continuous flow reactors. Okay, unsteady state operations of stirred reactors. Situations studied in this chapter where we have unsteady state operation include batch reactor, startup of a CSTR, and a semi-batch reactor. Let's talk about startup of a CSTR. If a CSTR is to be started up by introducing the feed and without having an overflow stream, so we will not have an overflow stream, we don't have that, meaning no output, then this is a semi-batch operation because you are continuously introducing an input but not an output. Therefore, it's a semi-batch operation. The startup of a fixed volume CSTR initially filled with pure solvent under isothermal conditions is rare but does occur occasionally. So now you can see that we have 2 modes of the startup of a CSTR, and as you know, during the startup or shutdown, the operation is an unsteady state operation. We can carry out an analysis to estimate the time necessary to reach steady state operation. Okay, so let's consider the liquid phase reactive system shown below. So here we have a constant volume CSTR which is going through a startup. The reactor is initially filled with the solvent only. Some additional information: the reactor is well mixed, so we don't have any spatial variation in the rate of reaction. What else? V equals VI, where I refers to initial. This I refers to initial. So the volume during the startup will remain constant. The volume of the reaction mixture during the startup will remain constant. So V equals VI. Right. What else? Epsilon, which is the reaction mixture density. Okay, so that's the density inside the reactor, the density of the reaction mixture inside the reactor, which would be the density of the leaving stream as well. What about it? It equals the inlet density, rho naught. Therefore, we will end up with the fact that epsilon equals epsilon naught. Okay, so as we said, where VI is the initial volume and epsilon naught is the feed volumetric flow rate. Type. Let's write a general mole balance equation for the given system for a species A. So let's write a general mole balance for species A. Of course, we want to do balance on a non-conserved quantity, so input minus output plus generation equals accumulation. Okay, so here we go. The input would be FA naught, right? So A is inputting into the system, minus output, which would be FA plus generation, which is the integration of RA dV from 0 to V, because RA is not a function of V, we'll end up with this, RA times V, equals accumulation, which is dNA by dt. Okay, conversion here does not have any meaning in a startup. Conversion does not have any meaning in a startup. Therefore, we said here during the unsteady state operation of non-batch reactors, we don't use conversion because it has no meaning. Actually, if I use it the way I define it, it will be wrong. So conversion does not have any meaning in a startup because one cannot separate the moles reacted from the moles accumulated in the CSTR. What does that mean? Okay, let's look at x. X equals FA naught minus FA divided by FA naught. Okay, assume now we don't have reaction, okay? And on my feed I have only A, obviously. And the reaction mixture or the reactor, CSTR reactor, is filled with solvent only. So as I put in A, and I said assume no reaction, I put in A, introduce A into the reactor. Now the quantity of A starts to increase inside the reactor. So there would be accumulation. So it's accumulating. A is accumulating within the system, right? Just like, for example, you are adding salty water, brine, you're adding to a tank which is filled with pure water. So eventually the concentration of salt inside the reactor will keep increasing until eventually it reaches the same concentration as that in the feed, right? So why is that? Because the salt is accumulating within the system. So the same thing with A. So if it's accumulating, that means that if A with time will increase, right? Because more A accumulating inside the reactor, its concentration will increase, and therefore FA will increase. However, I do have reaction. And as the reaction, or because the reaction takes place, the concentration of A should be less than expected, right? There is no reaction. So if the concentration is less, that means FA should be less, right? So do you see now? There are two factors affecting X. The accumulation with time, right? Because it's unsteady state, right? And the consumption, the conversion of A. Therefore, I cannot call this ratio X because this ratio does not represent conversion only. It represents two things. Therefore, it's wrong to use X during the startup or shutdown or an unsteady state operation of continuous flow system or of non-batch systems in general. طيب. So let's write the above equation here. Let's write in terms of concentration. Okay. So instead of FA naught, simply we will write CA naught times epsilon naught, right? And instead of FA, we're going to write CA times epsilon plus RA times V equals, instead of NA, we're going to write CA times V dt, right? Because the number of moles available inside the reactor, right? Because I'm doing the balance around the reactor. So accumulation will be accumulation inside the reactor. The number of moles inside the reactor is simply found from Ca multiplied by V, right? Okay, so let's see. Here we said assume constant volumetric flow rate. So epsilon equals epsilon naught, and we can take epsilon naught as a common factor, and then we'll have Ca naught minus Ca plus Ra times V, and here we have V being it constant, goes outside the derivative, dCA by dt, correct? And then we can divide by V. Let's divide by V. Okay, so if we divide by V, simply we'll have epsilon naught over V, that is 1 over tau. So 1 over tau Ca naught minus Ca plus Ra equals dCA by dt. Okay, so that's our equation written in terms of concentration. For most first order systems, so we're talking about first order system, right? We're not talking about first order reaction. We're talking about first order system, okay, which can be viewed by looking at the order of the differential equation. So this is first order differential equation, then this is a first order system. Okay, so of the derivative of the first derivative, then it's a first order system. For most first order system, steady state is achieved in 4 to 5 times the system's time constant. System time constant. Remember, I don't know if you have taken already dynamics or not, but tau p, which is the process tau, which is that time constant, okay, if you multiply it by 4 to 5, that would be the time necessary to achieve the steady state. If you did not take dynamic yet, so ignore this sentence that I have just said it. Okay, so that was about CSTR, startup of a CSTR with constant volume. Now we're going to talk about semi-batch reactor. Besides the startup of a CSTR in semi-batch mode, prior to achieving constant V, there are two basic types of semi-batch operation. So let's talk about semi-batch operation itself. We're not talking about the startup of a CSTR with no exit, which is a semi-batch operation. No, we're talking about semi-batch operation itself, intended semi-batch operation. We have two types. The first type is where we have removal of a product, which is known as reactive distillation. So for here, for example, we have A plus B gives me C plus D, and now this is the reaction mixture, contains A and B initially, but then we are producing C and D, and with a little bit heat, C will evaporate because it's very volatile, right? So I'm taking C outside the reaction mixture, so we have a continuous output, so that makes the operation semi-batch. Or the addition of a reactant. So again, the same reaction A plus B, but initially I charge only A. And then when the operation starts, I'm gonna add B to the vat, to the reactor. So now we have continuous input. We don't have continuous input and output, right? We have only continuous input, which makes it a semi-batch operation. So that's two types of semi-batch operation: removal of a product and where we have addition of a reactant. طيب. The first type of semi-batch reactor is reactive distillation. Reactive distillation. So I'm carrying out reaction and I'm also running distillation. That's why it's called reactive distillation. Here, reactants A and B are initially charged together, and one of the products is vaporized and withdrawn continuously. Let's say C in this case. Tamam? What are the benefits of removing one of the products in this matter? What's the benefit of doing this? What's the benefit of using reactive distillation? Well, for an equilibrium reaction, this will shift the equilibrium toward the right, increasing the final conversion. Correct? So, as we said before, if you pull one of the product out, the equilibrium will be shifted forward. Therefore, the equilibrium conversion will be higher. Therefore, you could achieve higher conversion. That's the first reason. Second reason, this will further concentrate the reactants and thereby producing an increased rate of reaction and decreased processing time. So when you actually remove some of the V, so the volume would start decreasing, correct? So if you decrease the volume with time, as if you are having higher concentration compared to the case where you are not decreasing the volume, when you are not removing C. So you will have, therefore, higher concentrations of A and B compared to the case when you are not removing C. Higher concentration will give you higher rate of reaction and will reduce the processing time. And finally, we prevent some side reactions. So if C was very reactive in such a way that it could react with D to form another product, or react with A or B to form other unwanted products, therefore here, if possible, it's better to remove C. So these are the benefits of using reactive distillation, not to mention that you're also getting almost pure C. Examples of reaction carried out in this type of reaction include acetylation reactions. So you have acetylation reactions and esterification reactions in which water is removed. So these are two reactions which can carried out in a reactive distillation. Type. In the second type of the semi-batch operation, which you said where one of the reactant is added, one of the reactants, example B, is slowly fed to a reactor containing the other reactant, example A, which has already been charged to the reactor. When this type of reactor is generally used? Any idea? Well, when unwanted side reactions occur at high concentration of B. So compare this situation where you have a semi-batch operation to a batch operation. For example, you would say, I will add all of A and B together. So if you add all A and B together in the beginning, you will have high concentration of B. And B could react with A in a different way to form an undesired product. Or B could react with the produced C or D to form unwanted, undesired reaction. So that's one benefit of using the setup. The other benefit, we can use the setup when the reaction is highly exothermic or highly endothermic. So imagine this reaction A plus B gives you C plus D is highly exothermic reaction. So if the concentration of A was high and concentration of B was also high, you will end up with high rate of reaction. That means high rate at which energy is released from the reaction, which means the temperature will shoot up. So you might not be able to remove this released heat. So the rate at which heat is released from the reaction could be much more than the rate at which you could remove this heat through the cooler. Therefore, the temperature will shoot up. Therefore, you will slowly add B. You will not allow B to be at high concentration. So you will slowly allow B, add B. Therefore, the rate of reaction will be slow as you can handle, meaning it could be run at a slow rate of reaction. Therefore, it will release heat at a low rate, and then this rate could equal the rate at which you can remove this heat. So you prevent the temperature from going up. In some reactions, the reactant B is a gas and is bubbled continuously through liquid reactant A. So in this case, we have also semi-batch reaction where one of the reactant is added. Example of reactions used in this type of semi-batch reactor operation include ammonolysis, so you're adding ammonia, chlorination, you're adding chlorine, and hydrolysis, reaction with water. Let's continue talking about semi-batch reactors. One of the best reasons to use semi-batch reactors is to enhance selectivity in liquid phase reactions. Why liquid phase reactions? Because it's popular, semi-batch reactors popular to be used for liquid phase reactions. For example, consider the following two simultaneous reactions. Desired reaction, A plus B gives you D, this is the rate law, and you have other possible reaction, which is an undesired reaction where A reacts with B as well, but this time will form U, and you have the rate law. The instantaneous selectivity, SD versus U, is defined as the ratio of the relative rates. So we look at the rates of the desired reaction, right? Compare it to the rate of the undesired reaction. Or we compare the rate at which D is formed, which is the desired product, to the rate at which U is formed, which is the undesired product. We call this the instantaneous selectivity because it's at that time. Okay, at that time where the rate is this much, where RD is this much and RU is this much. Okay, so RD, we have the rate law for RD, we have the rate law for RU, so we simplify it. Tamam, so here this cancels out with this, and this cancels out with this, so we'll end up with this ratio. Tamam. So now we have this ratio. How can we produce the most of our desired product and the least of our undesired product? How can we do this? Well, we can do this by at each minute, at each second, at each instant, we should have this value very high, correct? How can we have this value very high at each instant? Well, we can do this by keeping the concentration of Ca very high and the concentration of Cb very low. How do we do this? Well, simply by having a semi-batch reactor where initially you have A charged and then slowly you add B. So this way you make sure that the concentration of B inside the reaction mixture is always low. So this can be achieved through the use of a semi-batch reactor, which is charged with pure A and to which B is fed slowly to A in the vat. Right. So let's consider the liquid phase reaction. A plus B gives you C. That is to be carried out in the shown semi-batch reactor with a constant molar feed of B. So let's write a mole balance on species A. Of course, looking at A, we don't have A input, we don't have A output, so we have only generation of A. Therefore, we have RA times V equals the accumulation of A, which is dNA by dt. Okay? Okay, so that's for A. And please note that as we add B to the reactor, the volume starts increasing. So V is function of time, right? Okay, let's now write a mole balance on species B. So looking at B, you have B coming into the system, right? So you have input. So that is FB naught minus, you have B going out? No, we don't have, so no minus FB. Okay, so plus generation, so that is RB times V equals dNB over dt. Okay, so again, how do we write FB naught? Well, FB naught is simply CB naught times epsilon naught, and again V is a function of time. طيب, let's find V as a function of time. Right? That's what we want. We want to find V as a function of time because V is not constant this time. Okay, so how do you find V as a function of time? Which equation you are going to use? Are you going to use ideal gas law? Obviously not, because we have here a liquid phase reaction. So V is always related to mass through density, right? And we have very simple law, which is the conservation of mass, right? Continuity equation. Mass is conserved. Therefore, we can write an equation for mass, right? So input for the mass n dot n minus input of the mass, right, equals accumulation of mass, dm by dt. Which mass? The mass inside the system. That's the mass inside the reactor. Do you have mass leaving the system? No, we don't. We don't have mass leaving the system. So that goes to 0. How do we quantify the mass going in? Well, we can quantify it through density. Rho naught times epsilon naught equals dm. How do you quantify the m inside the system? Well, the mass inside the system is simply the density inside the system times the volume of the reactor, right? dt. And we know the volume of the reactor is changing with time. Okay, let's assume that rho is constant. So we have a constant density system. That means as the reaction progresses, the density of the reaction mixture inside the reactor is not changing with time. When this happens? Well, this happens when the majority of the reaction mixture is solvent, or if the density of A equals the density of B equals the density of C. Therefore, as the reaction progresses, the density does not change. Okay, so if we do this, then we have rho leaves the derivation, and we have this equation. Let's also assume that rho equals rho naught, constant density system, as we say. Okay, so therefore we can write instead of rho, we can write rho naught, and then we cancel out the rho, and then we have dv by dt equals epsilon naught. Of course, now we can integrate if we want. Okay, so let's integrate. dv equals epsilon naught dt, integration from time 0. At time 0, of course, v equals vi. V equals vi, the initial volume. And then we have at time t, v equals v, and therefore we have now the integration of dv is v, evaluated from vi to v, so that is v minus vi, and integration of dt is t, evaluated from 0 to t, that's t minus 0, t. Of course, epsilon naught is constant, not function of time, so we have epsilon naught t. So now we have an equation for v. Okay, so here we go. These are our equations. Remember, at time equals to 0. At time equals to 0. Na equals NaI. Remember, because we have charged all of A at the beginning of the process. So we have A inside the reactor, right? So Na equals NaI, right? However, at time 0, we don't have B inside the reactor because B will be added throughout the process. So at time 0, we don't have B. Okay, remember that, please. And of course, at time equals to 0, V equal Vi. So we use I, the not italic I, for initial, while we use the not for the feed, for the input. Okay, so this is our system where this reaction occurs. A plus B gives C, and it's carried out in the shown Semibatch reactor with constant molar feed of B. We derived all of these differential equations. This is a differential equation for A mole balance for A, mole balance for B, and total mass balance. Type. So you see now, for the semi-batch process, I'm preferring to work with number of moles, dNA by dt. Sorry, dNB by dt and dNA by dt. Of course, the rest can be written in terms of concentration because it's liquid. Three variables can be used to formulate and solve semi-batch reactor problems: concentrations, Ci, number of moles, Ni, easier for semi-batch, and conversion, X, but we have to be very careful. Okay, so we said we can write the mole balances in terms of concentration if I want, or in terms of number of moles, as we did, dNA by dt, dNB by dt, which is the easiest thing to do. Or we can also introduce X, but of course, if we use the conventional X, the ordinary X, the answer will be wrong, right? Because X, the way we know it, is wrong during an unsteady state operation. Okay, therefore my preferred way of solving these equations to keep them as number of moles, dNi by dt. However, say we want to write this equation in terms of concentration only. We want to convert dNA by dt to dCA by dt, and the same thing with NB. Okay, I'm gonna show you how to do this for A, and then you can do it for B by yourself. Okay, so let's look at the above equation. RA, well, RA is can be substituted for using the rate law, but in terms of concentration, so no big deal, times V as a function of T equals dNA by dt. Of course, we can write NA as Ca times V dt, correct? And here we can use the chain rule or the distribution rule, I think, and we can write the above equation as V dCA by dt plus Ca dV by dt, correct? And then we have here V dCA by dt plus Ca times dV by dt equals epsilon naught. So multiply by epsilon naught, and of course here you have RA times V, which is function of V. You can divide by V, so let's divide by V. Okay, and then we can take this term to the other side, so we'll end up with dCA by dt equals RA minus Ca epsilon naught divided by V. And of course, don't think of converting epsilon naught over V to 1 over tau, because tau here doesn't make any sense, because tau is only for continuous flow systems. Okay, so this is the equation that we got. If we do the same thing for dNB by dt, we get this equation. And again, remember, for this setup, where it was initially charged with A only, at time equals to 0, Ca equals Cai, the initial concentration, right? And Cb equals 0, because we did not have B inside the reactor initially at time 0. The subscript I refer to initial and not to entering. Don't forget that, please. If the reaction order is other than 0 or first order, or if the reaction is non-isothermal, we must use numerical techniques to solve the above equations, and we can use polymath, of course. طيب. Okay, فاصل إعلاني, commercial break. This is a very good article that you could read. don't act like a novice about reaction engineering. Don't act like you know nothing. Okay, when it comes to reaction engineering, if you got a project at work. So please read this articles available on Blackboard. Another article, overcoming equilibrium limitation in chemical processes. That's another nice article. So we talked about different ways of overcoming equilibrium limitations, right? When the reaction is, or when the conversion is limited thermodynamically, what we can do. So please read this article to reinforce your knowledge. Okay, with this we reach the end of chapter 4. Please complete the suggested problem set number 7 and make sure that you play the tic-tac-toe game. طيب, to conclude, in chapter 1, 2, 3, and 4, especially 4, we have learned and applied the following. Mole balance, we learned how to write mole balance. We learned how to write different rate laws. We learned how to utilize stoichiometry. And then finally, we learned how to combine and evaluate all the previous equations, whether we're going to evaluate it with hand calculation or using a PC, and all of this in order to be able to design an isothermal reactor. Is there anything else remaining? Not in chapter 4. However, in chapter 8, we will learn how to design the reactor if it was not run isothermally, which means we need to learn one more block, one more thing, which is the heat effect. We're going to learn it in chapter 8, not now. Okay, wish you all the best and see you then.